determine the minimum main breaker size for a multi-starter control panel containing multiple motors and a transformer, you must consider several factors and applicable sections of the National Electrical Code. Your calculation approach of summing the full load amps of all loads and applying a 1.25 multiplier to the largest motor load is a standard practice. Let's break down the process. Firstly, calculate the total full load amps. This involves summing the full load amps, or FLA, of each of the three 20 horsepower three-phase blowers and the primary current of the 2 kV amps transformer. In this case, the blowers each have a FLA of 27 amps, and the transformer has a primary current of 4.17 amps calculated by dividing 2000 by 480. The total full load amps is therefore 27 plus 27 plus 27 plus 4.17 equaling 85.17 amps. Secondly, apply the 125% rule. While the National Electrical Code doesn't explicitly state a minimum main breaker size for this specific configuration of a multi-starter control panel, it does provide guidance on sizing feeders and branch circuits for motors. Typically, the largest motor load is multiplied by a 1.25 to account for starting currents. In this scenario, since all three motors are the same size, you multiply 27 amps by 1.25, which equals 33.75 amps. Now, the adjusted calculation becomes 27 amps plus 27 amps plus 33.75 amps plus 4.17 amps, which is equal to 91.92 amps. Thirdly, select the standard breaker size. The calculated ampacity of 91.92 amps determines the minimum breaker size needed. However, breakers are available in standard sizes. The next standard size above 91.92 amps is 100 amps. But it's common practice to use a larger size for safety and future expansion, such as 125 amps. Now let's look at relevant National Electrical Code sections. National Electrical Code Section 430.22. V pertains to branch circuits for motors. It states that branch circuits shall be sized based on the motor full load current, or FLA, or locked rotor current, or LRC, whichever is greater. Since each motor has its own branch circuit with its own circuit breaker, contactor, and overload device, this section is relevant to the individual motor circuits within the panel but not directly to the main breaker sizing. National Electrical Code Section 430.26 addresses the feeder to a motor control panel. It says the feeder shall be sized to carry the maximum load that the panel is designed to carry. This section directly applies to the main breaker sizing. It requires that the main breaker be capable of handling the total calculated load of all connected devices. In addition to these code sections, consider a few additional points. Firstly, review the manufacturer's recommendations. The control panel manufacturer might provide specific instructions or recommendations for the minimum main breaker size. These recommendations should always be followed as they are tailored to the specific design and components of the panel. Secondly, think about future expansion. If there is a possibility of adding more motors or other loads to the control panel in the future, it's wise to choose a larger main breaker size to accommodate the additional load. This prevents the need for costly and time-consuming upgrades later on. Thirdly, consider voltage drop. Ensure the feeder conductors are adequately sized to prevent excessive voltage drop under full load conditions. Voltage drop can negatively impact the performance of the motors and other equipment connected to the panel. Fourthly, short circuit current rating. Verify that the main breaker and other components within the panel have a sufficient short circuit current rating, or SCCR, to withstand the available fault current at the installation location. This is crucial for safety and to prevent equipment damage in the event of a short circuit. In summary, your calculated minimum main breaker size of 125 amps appears reasonable based on the provided information. This accounts for the total full load amps of the motors and transformer, as well as the 125% multiplier for the largest motor load. While there is no specific code requirement for this exact application complying with the National Electrical Code guidelines, particularly Section 430.26, And considering the manufacturer's recommendations is essential. Always prioritize safety and ensure that all electrical work is performed by qualified personnel who are familiar with the National Electrical Code and local regulations. Remember to verify that the selected breaker is the standard size available from electrical suppliers. It's also beneficial to have a little extra capacity to handle any inrush currents or minor fluctuations in the loads. For instance, if calculations lead to needing a 90 amp breaker, choosing a 100 amp breaker could provide a buffer and avoid nuisance tripping. Furthermore, consider the ambient temperature in which the control panel will operate. High ambient temperatures can affect the breaker's current carrying capacity, so it might be necessary to upsize the breaker accordingly. Also, consider the type of loads connected to the panel. If there are any nonlinear loads, such as variable frequency drives, or VFDs, harmonic currents can be introduced into the system. These harmonic currents can cause overheating of the neutral conductor and the transformer. In such cases, it might be necessary to use a larger neutral conductor and a K-rated transformer designed to handle harmonic loads. In addition to the full load current, consider the inrush current of the transformer when it's initially energized. Transformers can draw a significant amount of current during energization, which can cause the main breaker to trip if it's not properly sized. To mitigate this, consider using a slow blow breaker or a breaker with a higher instantaneous trip setting. Also, consider the coordination of the overcurrent protective devices within the panel. The main breaker should be coordinated with the branch circuit breakers to ensure that a fault on a branch circuit will trip the branch circuit breaker before the main breaker. This helps to isolate the fault and minimize disruption to the rest of the system. Furthermore, consider the use of surge protection devices, or SPDs, to protect the sensitive electronic equipment within the control panel from voltage surges. SPD can be installed at the main breaker or at individual branch circuits. Also, ensure that the control panel is properly grounded and bonded to provide a low impedance path for fault currents. This helps to protect personnel from electrical shock and prevent equipment damage. Lastly, consider the labeling requirements for the control panel. The panel should be clearly labeled with the voltage, current, and short circuit current rating of the system. The labeling should also indicate the location of the main breaker and other important components. In conclusion, sizing the main breaker for a multi-starter control panel involves a combination of calculations, code compliance, and practical considerations. By carefully evaluating all of these factors, you can ensure that the panel is safe, reliable, and capable of meeting the demands of the connected loads. Remember to always consult with a qualified electrical engineer or electrician to ensure that the design and installation of the control panel comply with all applicable codes and regulations. To reiterate, your initial calculation is on the right track. Adding all the full load currents and then adjusting based on the largest motor's load is a standard method. However, it's crucial to ensure that all contributing factors, such as the transformer's inrush current, ambient temperature, and potential for future expansion, are taken into account. Always cross-reference with the National Electrical Code and the control panel manufacturer's specifications. Double-checking the short-circuit current rating, coordinating overcurrent protection, and implementing proper grounding are important for safety and reliable operation. This approach aims to provide a comprehensive understanding of the factors involved in properly sizing the main breaker for a motor control panel. Understanding these details ensures a safer and more efficient electrical system.